One more thing I want to say about chapter 18. When we go into chapter 18, we have to start worrying about higher order equations. So if we're looking at calcium phosphate and we're trying to get the KSP equation, this is going to dissociate into 3 calciums and 2 phosphates here. And so the KSP expression or equation is going to be the calcium concentration cubed times the phosphate concentration squared. Here. So if we assume none of this is dissolved at the beginning, we'll end up with a nice table like this, where 0 molar is 0 molar. In this case, I don't have any common ion. I'm not trying to do anything. I'm just going to let it dissolve in water. And what I'm going to get is I'm going to get plus 3. And so this is the amount that's dissolving in water. It turns out it's going to be plus 3s molar plus 2s molar. And so at equilibrium, I'm going to get 3s molar and 2s molar. This is where S is the solubility of calcium phosphate. And the solubility of calcium phosphate is equal to the molar concentration of calcium phosphate that it can get in solution. And the molar concentration, well, for every calcium phosphate I get 3 calciums. And so I'll have to take 1/3 of the calcium ion concentration. And so the calcium ion concentration in equilibrium is 3 times the solubility. Or the solubility is 1/3 the calcium ion concentration. The 1/3 factor comes from this, 1 mole of calcium phosphate for every 3 moles of calcium. And so that would just convert it back into calcium phosphate here. And it would be 1/2 the concentration of phosphate in equilibrium. And so when we're looking at the relationship here, if we want to calculate the KSP from the solubility, this would be 3s quantity cubed, 2s quantity squared. And so that would be 27s cubed, 4s squared, which would be 108s to the 5th. And so we'd have to measure the solubility, raise it to the 5th power, and multiply by 108 in order to get the KSP for this. If we have the KSP, which the KSPs are compiled in the book, we can calculate the solubility by just solving this for S. Here. And so we have to watch out because we get cubes now and higher order equations that we have to deal with. All right, we'll continue chapter 18 tomorrow. Today we're going to look at the lab for Thursday. The lab for Thursday deals with chapter 14. Chapter 14 is kinetics. And kinetics is the speed of the reaction. And so what we're going to do is we're just going to take some observations of reactions, how fast reactions occur. Not just how fast, but we want to see, what the rate looks like. And so, for example, if I'm looking at a particular reaction, the reaction we're going to look at is crystal violet chloride. Crystal violet, I'm going to abbreviate CV, and so this will be CvCl. When reacted with sodium hydroxide, the products that are formed are going to be crystal violet hydroxide and sodium chloride. And so what we're going to do is we're going to monitor this using the concentration of crystal violet chloride. And so initially we start off at some molarity of crystal violet chloride, and we want to see, after a certain amount of time, what happens to that. And so there are different things that can happen. For example, it's going to drop, as it reacts, but it might drop and then kind of flatten out. So it might be a non-linear type deal like this, where the reaction kind of slows down over time. Or it might be a linear reaction where it just goes down at a nice linear rate. And so what we want to do is we want to map out how this reaction proceeds over time, and that way we can make predictions. So for example, we can predict, after this much time, where do you expect it? Well, you know, after this much time where we expect it, we don't necessarily have to collect all the data. We just look at the curve. And if the curve is like this, then, you know, after this much time, we'd expect it to be here, you know, following this curve. Whereas if the curve is blue, then the reaction has long since been over. And nothing's been happening from this time to this time, right? And so what we're doing is we're just kind of mapping out how the reaction occurs so we can make predictions about, you know, how long it's going to take to react. And that way we don't have to sit and wait. So for example, we might just collect this much data here, and that way we can figure out what's going to happen later by just looking at the mathematical fit of the data. And so in the experiment, we're going to be collecting data on 2 runs at the different concentrations, and then just collecting data at concentration versus time. Now, how do we measure the concentration of crystal violet chloride? Well, it turns out it's pretty easy because crystal violet chloride is violet in color, whereas crystal violet hydroxide is colorless. And so what we're going to see is we're going to see the violet color fade. Now, violet is made up, you know, how do we get a violet color? You know, colors, where do colors originate from? At least, you know, for atoms, atomic spectra, color originates from electron transitions, then, or I don't know. Yeah, electrons falling from higher energies to lower energies, orbitals, orbital transitions. We call them electron transitions, right? In atomic spectra, we get sharp lines. For molecular spectra, we get broad peaks, you know, bands. That's because in molecules, things vibrate and rotate, and the energy of the orbitals change because of that. So we get a peak. Well, if something has a violet color, then there are different ways that violet color originates. And so we can look at the color wheel like this: red, orange, yellow, green, blue, indigo, violet. And so let's say if something has a green color, a green color can be made by mixing blue and yellow. And so if we have a 50-50 mix of blue and yellow, that's going to make green. Right? Likewise, if we have a mix of blue, indigo, violet, red, orange, yellow, then all these colors will mix to green as well. And so there are different ways, well actually, not those, but these. There are different ways we can make green. And so if we're to make violet, one of the ways to make violet is to absorb all colors except for violet. Another way to make violet is maybe mix red and indigo or red and blue. That should make violet. Another way to make violet is by absorbing yellow light. If we absorb yellow light, then all the remaining colors will add up to violet. Well, how can we tell how we made violet? You know, how's the violet and crystal violet made? Well, in order to figure that out, we're going to have to take the spectrum, you know, the visible spectrum of crystal violet. So let's do that here, or take a look at it here. All right, this is what crystal violet looks like. This is a chloride, so this would be crystal violet chloride. This is why we use the abbreviation, because the formula for crystal violet is going to be quite big. This is the name, which is tris-4-dimethyl-amino-phenyl-methylium chloride. but that's too much of a mouthful, so crystal violet will suffice. And the formula is quite long, so we'll just use abbreviated formula for it. This is the handout here, but the handout contains a lot of stuff in chapter 14, which we aren't going to worry about yet. So I only have the evaluation copy of the handout. We didn't buy this particular handout. But this is the visible spectrum of crystal violet. In fact, this is what we call the UV vis infrared spectrum, because the visible spectrum only consists of part of this range. Do you know what the range is in nanometers of visible light? Visible light ranges from 420 to 700. Is that right? 700. Okay, close. Actually, officially, the visible spectrum ranges from from 390 nanometers to past 700. We go all the way to 760 nanometers. And so this is the range of wavelengths for visible light. At wavelengths below 390, we call that what kind of light? Ultraviolet? UV? And at wavelengths above 760 nanometers, we call it infrared. And so visible light ranges from here. So at the edge of visible, right adjacent to ultraviolet, we have violet. And at the edge of visible, right next to infrared, we have red. And so infrared is beyond red, ultraviolet is beyond violet. And so what we're seeing here is we're seeing this big peak. This big peak is absorption of light. And so part of the rainbow is being absorbed. What part of the rainbow is being absorbed here? Well, if we map out the colors, we get red, orange, yellow, green, blue, indigo, violet. Well, this is kind of hard to see, so let's put it out here. It looks like this absorption peak. Do you guys remember lambda max? What does lambda max stand for? The maximum wavelength, lambda max? No. Lambda max stands for the wavelength at maximum absorption. And so we look at the top of the peak. It looks like it's going to be about, I don't know, it's 500, 700. So close to 600, right? Close to 600. What color light is that? And so if we just call it 400 to 800, and then 600 is right in the middle, right? And so this would be red, orange, yellow, green, blue, indigo, violet. It looks like it's going to be green-yellow light. If we absorb green-yellow light, then let's look at the color wheel. If we're absorbing green-yellow, then these colors are going to add up to violet. And so what we're doing is we're absorbing here, and then the color is going to look like this. And so crystal violet's violet because it's absorbing green-yellow light. That's the first thing. So what we can do is we can identify crystal violet based on the spectrum here. The next thing is Beer's law. Do you remember Beer's law? Beer's law says that the absorbance is equal to a constant times the concentration. And in other words, this is y equals mx. And so when I plot this, I should have a straight line with an intercept of 0. Right here. This is Beer's law. And I plot absorbance versus concentration. Here. But Beer's law fails. Where does Beer's law fail at? Beer's law fails at, this is absorbance at lambda max. Anyway. Beer's law fails at high concentration. At high concentration, it no longer is linear, but becomes nonlinear and just flattens out. And so Beer's law fails. Well, what is that concentration? What is high concentration? High concentration depends on what you're looking at, because it changes depending on what you're looking at. And so normally we don't look at the concentration. What we look at is absorbance readings. And so Beer's law tends to fail at higher absorbance readings. Well, what are high absorbance readings for Beer's law? High absorbance readings are around absorbances of 1, greater than 1.00. At absorbances greater than 1.00, then we start to get into the nonlinear. And so what we try to do is we try to keep the absorbances between 0 and 1. Because between 0 and 1, it's fairly linear here. Well, let's take a look at this absorbance here. What is the absorbance of this? When I look at the absorbance turns out to be it's like 1.5, 1.6, 2, 4, 1.5, wait, no. This is 0.5, 6, 7, 8, 9, 10, 1.3. That has an absorbance of 1.3, which means it's in the nonlinear region. And so what we need to do is we need to get this into the linear region. How do we get this into the linear region? We would dilute it. We dilute it to get a lower absorbance. Okay, now once we get the absorbance down to a lower number, like between 0 and 1, then we'll be in the linear region. And so this is what's going to happen here. If we're in the linear region, let's say this is 1.00. Here's our peak here. If we cut the concentration in half, then what's going to happen to the absorbance? So if we cut the concentration in half, the absorbance should be cut in half. And so what we're going to see is if the concentration gets cut in half, the absorbance gets cut in half. So this would have half the concentration and therefore half the absorbance. So this should be absorbed at 0.5. If we cut the concentration by a quarter, then we'll get 1/4 of the absorbance. If we cut the concentration by 10 to a tenth, we'll get 1/10 the absorbance. And so what we're going to see is that the peak height, that is the absorbance, is going to be directly proportional to the concentration. That's Beer's law. And therefore, we can figure out what the concentration is by correlating it with the peak height. And so when you did the Beer's law experiment in Chem 1A, this is exactly what you did. You mixed up different standard solutions and measured the absorbance so that we know, okay, this absorbance corresponds to this concentration, this absorbance corresponds to that concentration. We're going to skip that. We're not actually going to generate a Beer's law plot, although this handout says that we should. The reason we're not going to do that is because we know what this constant is. The constant is equal to epsilon times L times C, where epsilon is called the molar absorptivity constant, or the extinction coefficient. L is the path length of the cuvette. The path length of the cuvette, we can just measure. The extinction coefficient we're going to use this value. This is a value off Wikipedia. The extinction coefficient is 87,000 molar to the -1, centimeters to the -1. It would be better if we actually did it ourselves because of the variations, you know. But to generate a Beer's law plot is going to take way too much time, I think, and we're going to make this experiment shorter. And so we're just going to use the extinction coefficient off Wikipedia, and then plug in L, and then just measure the absorbances, and then convert those to concentrations. And so what we're going to do is we're going to monitor the absorbance over time. So maybe at 1 minute or 30-second intervals, we'll take the absorbance reading. And what we're going to see is that the crystal violet concentration is going down. And so we should be able to see the absorbance readings go down over time. And so when we're looking at a plot of absorbances versus time, we're going to see something like this. This would be the absorbance for crystal violet, and then over time we'll see how does the absorbance drop, because those absorbances will be directly proportional to the concentration. Does it drop in a linear fashion or non-linear fashion? That's what we want to see. And we want to map it out with enough data points that we can look at the mathematics of this reaction here. All right, so we're just going to run two reaction runs and collect the data for that. And then next week we're going to plot the data out in the computer lab. And so that's it. I'm not going to talk about the other stuff we're going to calculate for the lab just yet. We'll talk about that a little bit later. All right, any questions on this? You don't have to prepare your notebook because we're just going to set up the experiment together. It's actually pretty straightforward experiment to set up. And if you were to use this handout here, you're going to make your experiment a lot more complicated. No. You don't have to look at the notes. All we're going to do is we're going to come in and then I'll tell you what to do. I'll tell you what to do. It's not going to be as complicated as a titration because everybody's going to have the same interval. We're going to run, we'll talk about it on Thursday, but we'll collect the data then. Mm-hmm.
I swear, remember, I did it with bleach and ammonia. The rate of reaction.
Oh, bleach and ammonia? How did you monitor it?
There's a wipe and then a straw. And whenever you saw the rate that formed, he marked it.
Oh, okay. All right. And then you analyzed it?
Yeah.
Okay. Yeah, we'll do the same, except this one will just, actually the lab quest is just going to collect the data for us.
I remember the first order, second order, third order, catalyst.
Are we just gonna save everything on that lab quest and then we're gonna use? Are we using the lab quest?
We're using the lab quest, and then you're going to copy the data from the lab quest into your notebook. or if your phone has Wi-Fi, you can connect LabQuest to your phone and then
Oh, that's cool.
transfer the data.
Thank you.
I don't know. She brought it all in and I was like, I'll be in 3 minutes. I was waiting.
I know.